Welcome to this video. My name is Mark Scythian. The date today is August 18th, 2024. And this video is going to focus on why GM's air engine is not cost effective. So the number one flaw is that the cost to compress high pressure air into tank is exceedingly high, and so the remedy will at least be GM requiring to fund commercial grade air filling stations at reduced or no cost to the consumer, which is highly unlikely. So the claim is that it will cost 11.6 times more to fill the compressed air tank of GM's air engine automobile compared to the average cost per US gallon of gasoline. So the proof is as follows. So we'll take a test sample of 40 cubic feet of dry volume for a compressed air tank. Then we'll charge it to 700 pounds per square inch gauge pressure. So the first step is to convert the 40 cubic feet into cubic meters. So we'll just get the cube root of 40 cubic feet, divide the linear feet value into 3.28 to get meters, and then cube that value so we have a volume of 1.13 cubic meters. That's equal to 40 cubic feet. So assume that the atmospheric pressure is 14.12 psi at the average elevation above mean sea level of 1100 feet. So when we add the atmospheric pressure to the gauge pressure, we calculate the PSI absolute pressure, for which we can convert to pascals, 6894.76 pascals per PSI. So we have a pressure charge of 4.923 megapascals absolute pressure. Next, we can access the state equation, or the ideal gas law, which is PV is equal to nRT, that is the absolute pressure in pascals, times the contained volume in cubic meters, equal to the moles of ideal gas, in this case air is an ideal gas, times the universal gas constant R, times the fixed absolute temperature in degrees Kelvin. So the nRT part of the ideal gas law or state equation represents the potential energy of the gas measured in joules. So we'll replace the nRT with potential energy. Next, we'll just find the product value of the P times the V. So the given tank has a potential energy of 5.563 megajoules, or 5,563,765 joules of potential energy, or 4.091 million foot-pounds of potential energy. So this will be our test sample to compute the cost per joule across compressed air versus gasoline. So the maximum kinetic energy available, if total charge is instantaneously released, is equal to the potential energy. So this obeys the conservation of energy. Energy cannot be created or destroyed, but only changed in form. So assume commercial grade air compressor or compressors at the quote unquote GM filling station fills this quantity of volume to the pressure charge in a competitive consumer demand of 5 minutes. So let's just say that GM did support the product by providing GM filling stations so that commercial grade air compressors could fill at least this quantity and volume of tank to its 5.5 megajoules of potential energy in a time span of 5 minutes. So that is 300 seconds. So we'll assign T is equal to 300 seconds. So next we have the air compressor efficiency, whether it is light duty or commercial grade, is an industry average of about 65%. The AC motor efficiency across the industry is 85%. And AC electrical wiring will transfer electrical power, AC electrical power, at an efficiency of 96%. So the required power to fill tank at 100% total efficiency, as if there were no efficiency losses at the filling station equipment, based on 1 joule per second, discharge is equal to 1 watt of power. So we can divide the potential energy into 300 seconds. So at 100% efficiency, which does not exist, 18,546 watts, but then we have to find the reciprocals of each efficiency curve for each piece subcomponent as a product function. So when we make the computation, it will actually cost 34,966 watts of electrical power, AC electrical true power that is. We'll divide that value into 1,000 to get the kilowatts, and then we'll divide 5 minutes into 60 seconds to get the hours. So this is 2.9 kilowatt hours of electrical consumption, AC electrical consumption over 5 minutes. And then it costs 15 cents per kilowatt hour. But the filling station could not just pay for the electricity. It would also have to stay in business and make a profit and pay for all the other expenses like overhead costs, taxes, fees, commercial zoning. So in the real world, that will equate to selling that quantity of AC electrical power in kilowatts at 4 times the cost at a minimum. So it's $1.76 over 5 minutes to at least charge this tank's potential energy. And this is just a test sample, but what we're interested in is comparing this to the cost per joule potential energy across compressed air versus gasoline. So 1 US gallon of gasoline has a potential energy of 120,000 BTUs, and we know there's 1056 joules to a BTU. So 1 gallon of gasoline has a potential energy of 126.72 megajoules. 126,720,000 joules is the potential energy content in 1 US gallon of gasoline. And we know the average price per US gallon of gas in the US in 2024 is about $3.45. So it must be stated that that energy is relative and conserved. So energy is the capacity to perform physical work. So the joules per second compressed air discharge as a kinetic energy, including the BTU per second or joules per second of gasoline combustion, are relative. So the values and the numbers found in the potential energy of gasoline are transferable to any type of motion, whether we exchange that for compressed air kinetic energy joules per second or combustion joules per second from gasoline. So we're not going to get something for nothing. So whether that source is, that potential energy source is gasoline or compressed air, it's relative. So the next step is to divide the cost to compress air at commercial grade levels into that potential energy sample, and that would be the cost per joule for compressed air for the compressed air engine automobile. And so we do the same thing with the cost per joule for gasoline. So to put these very tiny values into scientific notation, we get 3.16 times 10 to the negative 7th power dollars per joule, or 3.16 e to the negative 7. That's a typo or a righto. And so these are restated as such. So the cost per joule for gasoline is 2.72 times 10 to the negative 8th power, or 2.72 e to the negative 8. So we will divide these two out again if we just check the work. So 1, 2, 3, 4, 5, 6, 7. And then, 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, and 8. So that's accurate. So we will divide these two values out, and the cost for compressing air versus purchasing gasoline is actually 11.62 times more expensive to compress the air compared to buying the gasoline. So it will cost GM or the consumer 11.62 times the cost of a US gallon of gasoline. So to get an idea what that amounts to practically, the statement is it will cost GM or the consumer 11.62 times the cost of a US gallon of gasoline to charge the equivalent potential energy of a US gallon of gasoline. So welcome to GM's air engine. Fill up your tank, 300-mile range for just, let's find out what this will cost. Average gasoline car mile per gallon fuel economy is 22 miles per gallon. So 300 miles divided into 22 is 13.6 US gallons. So we take 345 times 3.6 times 11.62. So welcome to GM's air engine. Fill up your tank, 300-mile range for just $545.21 per fill-up. Anyone interested in buying GM's Air engine car? So this is a possible disclaimer if it was sold. GM not responsible for filling costs. I don't know why they would be. Most likely disclaimer. So this has been an exercise in physics, thermodynamics, and fluid mechanics. With respect to efficiency and cost. Thank you for watching this video and have a great day.